Okay, so this will be our last topics under our chapter 1 discussion of EE126, and we will be using this more when we reach the some topics for the coming chapters. So now, before we discuss the what is gradient, divergence, and curl, first we need to define something. The delta, or they call it the nabla symbol. This is called the del operator. So this is called the del operator. So it's an operator, and this is a vector. Actually, this is a vector which is equal to the partial derivative with respect to x in the x direction plus the partial derivative of something, because this is an operator, so it's a partial derivative. This should be ay, then partial derivative with respect to z, az. So this is definition of del operator in rectangular coordinate system. So if we are in different coordinate system, it doesn't mean that the del operator will become, for example, in cylindrical, it will become the partial derivative with respect to rho, a rho, plus the partial derivative of with respect to phi, a phi, and z. So this is not true. This is not correct. Why? Because we cannot do that. We need to convert this vector, because this is a vector. We need to convert it using our methods that we did before in the previous discussions. So you need to convert them in terms of the coordinates that you want. So if you want it to be in cylindrical coordinates, then you need to convert this vector in cylindrical. You already know how to do that. You just take the dot product of that vector. So for example, if you want to determine the del operator in terms of uh, cylindrical coordinate system, then you just do the dot product of that in the raw direction. Then you get this will be the raw component, and so on, for the phi component, and so on. And that's how we convert it. But this time, let's look at first the rectangular coordinate, the del operator at rectangular coordinate. So first, what is a gradient? In basic math, in calculus, when we say gradient, this is somewhat synonymous with the change. Change. Gradient means change. Or, in other words, this is a slope. In two-dimensional, this is just the slope of a certain function. Here, we are now in three-dimensional. So instead of calling it a slope, we call it a gradient. This is actually the gradient tells us the direction of the maximum change of a field. So if you have a field which is a scalar field, by the way, gradients is also used to convert a scalar quantity or scalar field into a vector quantity. So if you take gradient of a scalar, you get a vector because it's a direction. It tells us the direction of the maximum change. What do you mean maximum change? So for example, if I have a surface here, somewhere at the xy plane, then this is a source of a maybe it can be a heat source, it can be a charge, and so on. It's a source of, this is a surface area. So this is a scalar field. This is a scalar in terms of scalar quantity. So that we can just call it f of x, y, z. It's a surface area. So now, if this is a source, then if I measure, if I compare something from this surface area to another point outside that, then the difference between the two, if you find the maximum, the direction of that is actually the gradient. This will be the gradient. or we can just call it grad of f, or del of f. So the direction usually is always in perpendicular with the surface area. Why? Because the maximum will always be in 90 degrees, because that's the maximum angle or maximum slope that we remember. So if you have a slopes, if this is line 1, this is line 2, and this is line 3. So these are three lines. The maximum slope will always be the 90 degrees, because this is actually with the infinite slope. If you remember in analytic geometry, and if it's that line, then the slope of this is 0. So our maximum is always perpendicular with the surface, the source of the surface. So if you want to determine that, so that will be a vector field. So if you want to determine the at that point, then you just substitute the point in the vector field, then you get the actual value for the vector or the gradient. So now let's apply this gradient. How do we evaluate a gradient? So if we have a vector or a scalar field f of x, y, z, y, z. So this is not a vector. So we want to determine the gradient of this. So to determine the gradient of this, we just take the product of these two. So what do we mean by this? We just need to take the partial derivative of f with respect to x in the x direction, plus partial derivative of f again with respect to y in the y direction, and lastly partial derivative of f with respect to z in the z direction. So this will be the equation of the gradient of any vector, or any surface, or any scalar field. You just take the partial derivative of that with respect to d directions. So this is gradient. Before we go with the other coordinates, let us look first for the divergence and curls in rectangular coordinates. Let's just focus on rectangular coordinate system, because later on, if you want to convert them, you can already solve the transformation, the conversion of these vectors, because you know how to convert. These are just vectors. You just convert them in the coordinates that you want, in the system that you want. Next, for the divergence. So if a gradient, the output of a gradient is a vector. A divergence is the other way around. The output of this is a scalar quantity. What does it mean? What does divergence mean? So, for example, if we have a vector field in xy plane, let's say this is xy plane. The direction of the vector is, let's say the vector is x times ax. So it increases, the magnitude increases when we increase the value of x, and so on. So if this is the field, the given field, let's call it f, because this is a vector field, f, x, y, z. Then a divergence, when I take a point, a circle, draw a circle around this. If you compare the amount of uh, a vector that is entering the circle, and the amount of the vector that is leaving the circle, we have two ways where of doing that. So what will be, if we compare the field strength? So for example, this is just f equals x, ax, in the direction of x. So this is x. So it increases when we increase x. So here, let's say if this is 3 and this is, let's say, 4. So if we compare the strength at this point and at this point, so this is just 3, this is 4. So the one that are leaving the circle are greater than, the strengths are greater than the vector that are entering the circle. If this is the case, then this is what we call a positive. This is a positive divergence. So you get a positive divergence. Divergence. If the other way around, if the number or the strength of the field, so if, let's say if we take the opposite direction, negative x, ax, that will be in this direction. And if you compare it again, so we have a circle. Now this time, the strength of the vectors that are entering is now greater than the strength of the vector that are leaving the circle. So if this is the case, then we have a negative divergence. And what happens if the strength of the field or the vectors that are entering are equal, the same as the strength of the vectors that are leaving? We call that a zero divergence. They are zero divergence. That's the time when you get at zero divergence. So it means the divergence, the strength of the field that are entering that circle is the same as the strength of all the field that are leaving the circle. Now, how do we evaluate this divergence? Divergence, div, divergence of a certain vector f of x, y, z. So this is a vector. So if you get the divergence of f of this is the same as the dot product of the del operator with that vector. So if we take the dot product of that, so we have the del operator here, partial derivative with respect to x, ax, plus partial derivative with respect to y, ay, plus partial derivative with respect to z, az. You take the dot product with that vector, f. So we have a vector, let's say the components of the vector are f of x, ax, plus f of y, ay, plus f of z, az. So if we simplify this, the divergence now will be equal to, by applying that product, you just multiply the components. So this will be the partial derivative of f of x with respect to x, ax dot ax is 1, plus partial derivative of f of y with respect to y, plus partial derivative of f of z with respect to z. And this will be a scalar quantity. It has no direction. It can be negative. It can also be negative, but the meaning of that negative will be this one, the strength of the leaving or entering is greater than the strength of the leaving vectors in that circle. So this is divergence. Then lastly, for the curl, if you have a vector field again here that is gradually increasing, let's say when we increase the value of y, all x also increases. Then if I put something, let's say a black here, what will happen to this black? So if this is a force, then we have a block of wood. If I apply a force at the end, so if you compare the force here and the force here, the force at the upper part is greater than. So if we do that, the lesser the force at the bottom side, then what happens? The wood or the block will rotate because the force at the upper part is greater than. And that rotation is called the curl. That's the curl. Now, if we have a vector that has the same magnitude, then if we again put here a block, so the block will not rotate. And this field, this is called a conservative field. Conservative fields. It's like what we discussed in the line integral. It's conservative when the total energy use is equal to 0. because there's no energy that is being used here. So it will be considered a conservative field. Unlike this one, because the black will be rotating. So that's curl. Now, how do we evaluate that? So if divergence is the dot product of the del operator with the vector field, then curl is the cross product. This is the cross product instead of that product. So again, if the components of f are f of x, fy, fz. So if we evaluate this, this is just equal to ax, ay, az using this notation. Then we have partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And we have the components f of x, fy, and fz. So this is how we calculate the curve. And the result for this will always be a vector quantity. We can actually evaluate this. Let's try to evaluate. Copy. Let's just simplify this. Ax fy. We have these are positives. These are the negatives. Then we can multiply them. The result will be, this will be a partial derivative of fz, partial derivative of fz with respect to y in the x direction. So this is for the positive. We have partial derivative, this is f of x plus partial derivative of f of x with respect to z and the y direction. Then this one, partial derivative of f of y with respect to x in the z direction. Then we subtract. So this is minus, 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 and this will be the partial derivative of f of x with respect to y in z direction, in the z direction, plus partial derivative of f of y with respect to z in the x direction. Then lastly, partial derivative of f of z in the x direction with respect to x in the y direction. Then if we subtract the components, and each component, for the ax component, we have partial derivative of f of z with respect to y. Here we have minus partial derivative of f of x minus partial derivative of f of x with respect to y also. So these are in the z. This is wrong. This should be, this is not ax. The ax is this one. Plus or minus partial derivative of f of y with respect to z. This is in the x direction. Plus for the y direction, we have partial derivative of f of x with respect to z minus partial derivative of f of, where is this y? F of z with respect to x in the y direction. And lastly, for the z component, partial derivative of f of y with respect to x minus f of x, partial derivative of f of x with respect to y in the z direction. So this will be the curl of the vector f. So this is how we compute for the gradient, divergence, and curl in vector analysis.